Good afternoon, everyone. Thanks for the chance to speak today. I feel a bit like the Eye of Sauron up here at the top of the tower. My name's Jim Seale, and I'm a final year graduate student in Fraser Stoddart's lab at Northwestern University. I'm going to be talking about the interface of polymers and molecular pumps, including micelles, by the way. First, I want to talk about the definition of molecular machines, because the definition that we use in the Stoddart group and in other groups such as the Feringa group and the Lee group and many others is a little different to the definition I think that's implicit here with the molecular machines. Our definition centers around unidirectional motion. In the case of this molecular pump that I'll be talking about more today, we're talking about the unidirectional motion of the ring along the thread molecule, along the pump. Here's another recent example from the Lee group and Stefan Borsley, who's in the audience back there. And it's a rotary motor. And this is a small molecule where one part of the motor can rotate with net unidirectionality relative to the other part. You often see enzymes and other synthetic machines called molecular machines, but by our definition, they wouldn't be. I think there are, of course, certain enzymes that do count as molecular machines by our standards. For example, transmembrane pumps like the sodium-potassium pump that pump ions into membranes. But most of the time when people talk about enzymes as machines, they just mean a very complicated catalyst. And another example that demonstrates the fine splitting of the definition is in terms of molecular switches, such as this simple azobenzene. Molecular switches we would not consider molecular machines because that transition or that change between the trans and the cis isomer doesn't happen with any net unidirectionality. And the reason that that's important is that if you don't have the unidirectionality, you can't generate an away from equilibrium system based on molecular motion. So the slide's a little bit messed up, but I just want to talk about the mechanism of our molecular pump here. It forms a ritaxane, which is a linear molecule on which you have a ring threaded, and it forms a stable molecule. What I'll do in a practical sense is I'll start with this molecular pump, the thread molecule up here. This was originally developed by our group in 2017, and it's become the blueprint model for all the subsequent studies. And I'll mix that in solution with the cargo of the pump, which is this ring here, the cyclobis paraquat p-phenylene rings. When you then reduce the system sufficiently, you form a strong host-guest complex between the ring and the binding site on the pump cassette. When you oxidize the system back to the ground state, the ring is then induced to leave the binding site, and this it does with net unidirectionality moving towards the right as shown, where it ends up trapped, mechanically interlocked on this short chain here. One key feature of this pumping system is that the ring, once it is pumped, is now stored in a metastable state where it has a higher energy than it did when it was in free solution. And we've applied these molecular pumps to the formation of polyritaxanes. Polyritaxanes are just polymer threads on which you have threaded multiple different rings, like the beads on a necklace. This was done originally by our group for polyethylene glycol polymer chains. That was reported by Yunyan Cho of our group in 2020. And then I did a follow-up work that was reported last year, doing something similar with polypropylene glycol, a more bulky and hydrophobic polymer chain. And effectively, when you have a pump on either end of these linear polymers, you can perform these redox cycles to pump precise numbers of rings onto the polymer chain. So if you want the polyritaxane with 2 rings, you perform 1 redox cycle in the system. If you want it with 10 rings, you perform 5 redox cycles. And so I realized when I was making these slides that this, in a slightly alternate sense, does conform to one of the goals that was listed in the agenda for today's meeting. That is reprogrammable tools that can create individually specified chemical bonds. When I'm talking about individually specified chemical bonds here, I think in the original sense they're talking about the Drexler-esque positioning of individual atoms to form presumably a covalent bond. In this case, I'm talking about the formation of a mechanical bond. There is a stable entanglement between the ring and the thread. And for reprogrammable tools, I mean that in a quite literal sense, that I will program this on a laptop, and in an electrochemical setup that performs the redox, it will generate the products as desired. Practically, what I'll do is well, I'll start with this electrochemical cell. We call this a H cell just based on its shape. It has a membrane here in the bridge that divides the two separate cells. When we mix the polymer chains with the pumps, with an excess of the rings in the working cell, and then a sacrificial electron source in the counter cell in solution, we can then just perform redox cycles with a potentiostat hooked up to a laptop and produce the desired polyuretaxane. So for example, if I want to pump 4 rings onto this polymer chain, I will get a trace that looks like this. This line dropping down is showing an increasingly negative charge. So that's as we inject electrons and reduce the system. It is then sufficiently reduced after about an hour, and we remove the electrons by applying the opposite potential. That completes one redox cycle, which pumps 2 rings. So in this case, to pump 4 rings, I simply perform this cycle twice. Similarly, if I wanted to pump 8 rings, I would just effectively do the first process back-to-back to get a programmed synthesis of the polyuretaxane with 8 rings. My current direction is to try to attach these molecular pumps to an assembled dynamic matter. In this case, I've chosen a micelle. So we have this previous work that studies the abilities of these pumps to operate on polyethylene glycol and polypropylene glycol. And as it happens, when you combine these two different kinds of polymers into a triblock copolymer of this form here, these are called pleuronics. They're well studied and known to form micelles in aqueous solution. So this is a cross-section of the spherical micelle that can form. The polypropylene glycols, which are hydrophobic, are buried in the micelle interior, and the pegs are left on the micelle corona. My current goal is to attach the molecular pumps to these pleuronic chains and then see if they can be integrated onto the surface of these micelles. And we're interested in this because if you talk to anyone who works on these kinds of molecular pumps, what we really want to do is put them onto vesicles or onto liposomes in order to mimic the transmembrane ion pumps that are abundant in nature. And so this is just one practical route that we see towards that eventual goal. With that, I will thank the group members, many of whom have been associated with Foresight over the years, including Yunyan Cho and Liang, her former members, as well as our former fellows, as well as Yuaning Feng, who's here and will give a presentation later on. And also thanks for your attention.
Thanks, it's interesting work. When I think of getting, like, let's say a macroscopic pump that I would buy from a manufacturer, they would give me some kind of a spec sheet that would say something like, if you use this much power, you can pump this much flow rate against this much pressure difference. Say, kind of, give me that kind of a range. Is it yet possible to get that kind of information about the pumps that you were talking about in something that you basically can think of it as a spec sheet for a molecular machine like this?
Yeah, that's a great question. I think what we would be looking for there is the chemical potential of the pumped rings once they are trapped on the polymer chains. And we don't know a way to study that yet, and we haven't worked that out. All we know is the input energy that we have to put in. Like I was showing on the graphs there, we have the exact charge. In terms of what it's capable of, I think we've still not pushed it to the limit. Yeah.
Hi. I think the micelle direction is really cool. Have you considered how you might impart some asymmetry to that system so when it does pump, there's some net force displacement to it?
What do you mean by
For example,
asymmetry?
if the pumps were sort of, radially distributed and they were reacting, you wouldn't get a net force from that system. But if you could have a micelle that had some polarity to it, then it might move as a result of that process.
I'm not sure I quite understand. Yeah. Do you think you could phrase the question another way?
Okay. My colleague here is saying that there might be a concentration gradient present in the system, and that might be the source of the asymmetry in your system. So that sort of helps answer my thought
Okay, yeah. I mean, when we pump these rings onto the chain, we generate a high concentration compartment of those rings. So I think there you're already using the energy to generate a potential energy, right? Those rings would rather be off the chain and back in free solution. We don't have a great way to measure what that would be yet, but we know because if you actually degrade those pumps, the rings will all spontaneously re-enter solution. So we have that as a kind of proof that they're in a metastable state when they're on the chain.
Okay, thanks.
Yeah. Yeah.
Can you make the chains long enough to programmatically induce color?
Lose color?
Make the chains like 600 nanometers so you get color.
What do you mean by color?
I've seen a similar paper where they have like side chains on a backbone, and essentially it's a stretchable material. When you stretch it, it changes color because it interacts with light of a different wavelength. So I feel like you could stretch it by making it like about 600 nanometers long.
Okay.
400 to 600, whatever.
Yeah, I think I understand. Probably you're talking about mechanophores, where they pull and then it changes the color. But that would depend on the nature of the polymer chain. So in this case, we're using polyethers that are just colorless. Although the rings that we pump on do have color, so in that sense, they impart color to the system. But I think it's a great point. We do have one paper where we have a fluorophore that is part of the chain, and then rings are pumped on, and they're able to quench that fluorescent activity. So the proximity of the rings in this kind of nano-confined environment can change the spectroscopic response of the material.
So for the sake of the schedule, I'm going to call it there, but we are going to a break, so if you want to ask more questions, this is the opportunity to talk.